Welcome back to my office. From here I can control the different radio telescopes of our observatory. They are at the moment in different observation programs, so they point to sources in the universe which send radio waves. These sources are in our case quasars, and everything what you see here, for example, the controlling, the web interfaces, the conversion of coordinates, for example, that you have the coordinates in right ascension declination, and you have to convert it to a local position to point in azimuth elevation. Also, the controlling of the automaton so that the telescope points to this source and so on. Everything is based on programs. And the internal heart of a program is an algorithm. So therefore, we have to think about the algorithms, about the performance of algorithms, about the different classes of algorithms, because they can be fast or they can be solvable and they can terminate or not. So everything what you write in your programs is based on this algorithm. So please follow me to the next lessons about algorithms. Welcome again to the next lesson about algorithms. So until now you programmed a lot of things in the tutorials, and everything what you did there was developing of algorithms, and therefore we now have to understand the inner heart or the general principle of an algorithm. And also, if you remember that you programmed these searching algorithms, and if you did this, and if you also measured the time, then you saw also the general principles of the runtime behavior. So you saw something like a linear behavior for the sequential search, and you saw something like a constant behavior for the index-based searches. And therefore, you have two classifications in the efficiency, and therefore you will have also a classification of algorithms, and this is what we want to do today. So therefore we will have a look into these different things. First of all, we have to understand what is an algorithm. Then we will have to look into how can we define the efficiency and performance of an algorithm. And then we directly come to a theoretical definition of the efficiency, so that you can identify the class of an algorithm, of the performance of an algorithm, even if you don't run it, or if you have some influences from other programs, like you have seen in your programs of Matlab, if you measure the time period of a runtime. And if you have this big O notation, we will have a look into different special algorithms focused on sorting of data, and therefore you will also have a look into things which is named a recursion, so a functional method where function call itself again. And then we will have a look into performance and correctness of measurements. Let's start with the first thing. What is an algorithm? An algorithm in a general way defined is that you have a finite sequence of well-defined, distinctive steps or instructions to effectively solve a task or even a class of tasks in a finite length of time. So if you focus onto this definition, you will have three different things which you have to view on. The first one is the finiteness, the next one is the definedness, and the next one is the visibility. Other things which you might take into account or where additional useful constraints are that an algorithm is an abstraction. So it is better to solve a class of tasks instead of just one special case or one special task, because then you have a general solution. And then there is the point on determinism. I split determinism into two parts. One I call deterministic and another one I call determinism, because it is slightly the same but has small different viewpoints. Determinism is that you have only one possibility of a next step. So it's not that you jump between the different next possibilities from one situation. So if you think in state charts, you have only one really defined condition to jump to the next state. It's not that you individually decide or that you randomizely decide which way you go. And the other one is the deterministic, which means that each run with the same starting condition will lead to the same sequence and also to the final state, to the same final state, so that you don't have something like chaos. Both things are slightly connected to each other. One is more focused on the step, on each decision, and the other is that you always come to the same end situation. The final end situation is also that you have a termination. Remember the graph theory, which we explained in the lessons before. In the graph theory, you had the situation that a finite set of states and edges can lead to a situation where you repeat things several times so that it might never end. Therefore, it is necessary that this finite sequence will also come to an end so that the final state will be reached, and it will be reached in a finite time interval, so that it will be ended in a time period which will be realistic. And then it should also use a special limited number of resources. So if you need infinite resources, it's also not a well-defined algorithm. So only a finite set of resources must end or must terminate in a well-defined finite time interval. It must be deterministic, and it must also be programmable. So you can convert it to a machine code or into a computer program. And therefore, if you read all of these things here, then you see that algorithms, or the general character of an algorithm, is completely independent from a programming language. So you can solve tasks on your paper and then you convert it to a program. Therefore, it's completely independent. The programming language must be able to realize an algorithm, to implement an algorithm, but the algorithm or the internal character of an algorithm is completely independent from a language. And therefore, you can describe algorithms with different ways. You can use a textual-based method, so an instruction set like a normal text sequence. You can use a mathematical description like a function where you have arguments. a function name and you have return values or a return value. You can describe an algorithm or a sequence or a behavior with conditions with a graph. You already learned this with the state charts, with the state graphs, things like that. And you also can write pseudocode or real instruction in a programming language, so that you have different possibilities to describe what an algorithm should do. The next thing, as we know now, what is an algorithm, what is the internal character of an algorithm, is that we take care on the comparison of algorithms. So how good is an algorithm? You can define a sequence of commands. You can define a sequence of instructions, but is each sequence equivalent to another one, or is there a difference? And the difference is in most cases the performance. And therefore the next step is we take a look into the definition of efficiency and performance. And here I do two different things. So the first one is we take a very theoretical identification so that we can understand the general class of an algorithm. In any case, we take each instruction as a time of 1, so that we know if we have 10 instructions, we have 10 time units. It's not the real time what it needs or what it is needed for. So, for example, if you have a function which costs more time, or if you have things which cost more time due to accesses to the memory, then the real performance or the real behavior is different. But the general class is always the same. So if you do the larger instruction set, more often you have only a linear constant which you add, but the general behavior is the same. And therefore I split into two evaluation methods. The one is the efficiency, the complexity or efficiency of an algorithm. We will come to this big O notation. And the other one is the performance. So this is more the theoretical inspection of an algorithm, and this is really the benchmark or the practical inspection of an algorithm, or the realization. So there's a difference from here. This is more or less the theoretical algorithm, to here, which is a realization, a practical realization of the algorithm. So again, what do we do? In the theoretical evaluation, we have a general classification of the algorithm. We count how often an operation is operated, how often does it occur in combination of the number of items which are touched, and therefore we get a theoretical understanding of the class. On the other hand, we really measure an implementation under a predefined test circumstance, which means we do a benchmark. This is the runtime behavior, and therefore we do a real world scenario. Other things which we can also observe is that we take care on things like time against space. So, for example, we can focus on runtime, or we can focus on the resources which are used. So if we focus on runtime, then we think about how many steps are required, are there possibilities to reduce the number of steps, and how long does it take. So this is the time inspection. Here we focus on resources, how many states must be defined. So how long is the program, how much space does it take in the memory, and therefore how much space is used also for the realization of the different types and things like that. And we can also focus on the worst case scenario, which is here, or on the average case. So the worst case is also quite nice for benchmarks. Remember what you did maybe in your tutorial for the different search mechanisms. In base case, you search the first element or the last element, so that you can combine or the last element, so that you can combine how long does it take for the first element and how long does it take for the last element. So these are the worst cases. Also things like data which are not part of my raw data set. So therefore here we focus on the critical situations. On the other hand, for the most situations, we'll have a general behavior, so the average or the mean behavior. And therefore we focus on the overall situation. So the general situation, if we search a general element or a general key, and we calculate the mean here, more or less, the mean behavior. So these things we will do, and therefore if you focus onto these different things, you will see if you go onto the theoretical parts on the complexity and efficiency in the theoretical part, you will identify the class. So the general class, it's not a real implementation, so it's not that you can directly say, okay, it will last 10 seconds. It will just identify that it is a linear behavior, that it is a constant behavior, or that you have an exponential behavior. It's a theoretical observation. You more or less focus on these constraints of time, and in most cases you focus on the worst case scenarios, because then you can compare the behavior of the different algorithms, so that you see in the worst cases how efficient your your algorithm, your general class of the algorithm is. For example, if you do ciphering and you compare different ciphering mechanisms, you will check how is it in a worst case scenario. On the other hand, if you do the benchmarks, then you really focus on the performance, and then you do a benchmark in a real world scenario. And here you can focus on both. It's not so interesting if you have a theoretical class, then you can focus on how long does it really take with my realization of or implementation of the algorithm, and how resource hungry is my implementation. And therefore you mostly focus on the average case. You can also go into your worst case scenario, but usually you focus on the average case. So if you do a request, or if you do a questionnaire in a search engine, you focus mostly on the average time and not so much on the worst case scenarios. With this, we can go into details, and we can directly, first of all, focus on the theoretical part, the efficiency, where we come to the so-called big O notation. What is the big O notation? As I already mentioned, we now focus on a classification. So therefore we don't focus on a very single problem. We try to understand a general complexity class, so according to a problem size n. So therefore we make an assumption that all steps cost equally. So each instruction has a cost of time of 1, for example. So that we count the number of instructions, and therefore we count the number of loops, and we identify how many steps are required with a cost unit of 1. This means that adding a constant number of instructions, so that we add a sequence of instructions to the existing thing, which does not change which does not change with the problem size n, so that the problem size is the same, does not change the efficiency class at all. It's just if you add additional instructions to the same problem size, to the same problem class, it just changes with an offset, so it keeps the same class. And therefore, the big O notation defines the classes ignoring constant factors or insignificant details. So we don't focus on details of realizations, for example, or on constant offsets in our runtimes. So if we add additional instructions, which just changes or shifts in a constant way, will not be part of the big O notation. We just want to identify, okay, it's constant, it's linear, it's exponential, and so on, or logarithmic, or whatever. So therefore, we identify with this big O notation a general class, and the class is named O of, and then in the braces you have the general class behavior. So if you have a 1, then it means that it is a constant complexity. You don't write O of 10 or O of 20 because this is just a constant offset, and a constant offset is not part of this inspection. So therefore, what you do is O1 are all of, or O of 1 are all of the constant complexity algorithms. So what does it mean? A problem with 1 element costs exactly 1 instruction. A problem with 2 elements also costs just 1 instruction unit or 1 time unit. And a problem with n elements even just costs 1 instruction or 1 time unit. So you can have as many elements as you want, and you always will need 1 instruction. If you have a O of n, it means you have a linear complexity. A linear complexity means that if you have 1 element, you will need 1 instruction or 1 loop run. If you have a problem with 2 elements, you will need 2 runs or 2 instruction units. And if you have n elements, then you will have n instruction elements, so that you have a linear growing performance. And if we watch a special example, then you will see that in some cases, and it's really just in really rare cases, it's possible to convert linear complexity into constant complexity and vice versa. So that, for example, if you optimize your algorithm already in a theoretical way, so that you change the general class, then even also the problem solution in a programming language will be much better. This is what you want. So if you understand the general algorithm characteristic, then you can also write a very efficient code. And therefore, here's an example where we do the sum of the first n natural numbers. And if you do it in a normal way, it's here on the right side. So if you go to this here, this is the normal sum. So what do? We do something like an iterative addition. So we take the first number here, and then we add the second number. We take the result, and we add the next number, and so on. So this means for 1 number, we need 1 operation, or in this case, 0 operations. For 2 numbers, we need 1 operation. We add 2 numbers. For 3 numbers, we add 3 numbers, which means we have 2 operations, and so on. So you see, you have here a linear growing. So the iterative way is a linear growing. But the same can be done with also constant growing, because if you always take this sum here, so for example, that you calculate n times n plus 1 times 0.5, then you also calculate the same result. So if you compare this result to here, but you always will need 1, 2, 3 operations. And it will not change if you have a change in the number of elements. So if you sum up 10 elements, you will have the same situation. And if you sum up 20 elements, you will have the same situation in time units. So if you implement this, it will be in a constant behavior of the time. So this means also benchmarks will always need the same time in real world scenarios. And here, if you implement this, then you will have these linear behaviors. Also, a linear behavior in the programming. And therefore, it's a simple example where you can convert between linear and constant behavior. The only thing is that you have to check if this really calculates the same for all solutions. Because if you do the first 10 elements and you say, okay, it's the same, then it's not really a proof, because it can happen that, for example, an element 100, or if you have 2000 elements, that there can be a difference. In this case, it will not be, but it can be. And therefore, you have to do a proof that the left part does exactly what the right part does. And here you can use, in this case, the mathematical induction. So what you do is, you have this and you want to prove that this is really the sum of all elements for all elements. Therefore, you start with the first element and you check if it is correct. So you take this and you take the first element, which is problem size 1. So you have one element, and then you enter 1 into your calculation. So it means you have 0.5 times 1 times 1 plus 1, and this means you get as a result 1. And this is true in this sum calculation. And then you have to abstract it and generalize it so that you say, okay, what is for the next step? And for the next step, it is that sum for n plus 1 is the sum of n. So the sum for the n, which for example is here, for 1 you have already done, plus the next element. And if this is again correct, so if this results again in the same formula, just with n plus 1, so with the next element, then you know that it will be correct for everything. So therefore, you replace the sum n here with this, and then you just multiply and change your mathematical equation so that at the end you will get 0.5 times n plus 1 in parentheses times n plus 1 in parentheses. And if you compare this with this, then you see that at each position where you have an n here, you have now the n plus 1. And this means that for n plus 1 you have the same equation, the same calculation like for n. And this means, as you have now an abstracted class or an abstracted problem size, you know that for each different numbers of n, you will have now a correct result. And therefore you know that this really is the same like this, because what you do here is exactly the same like here. You add to an existing sum, so iteratively, the next element. So this is quite nice. We know now that this sum really implements this sum, and therefore we can convert from a linear complexity to a constant complexity. And this is not really often the case. So it's not possible that you convert things into easier complexity or into a faster efficiency. And therefore, we should have a look into different other things. For example, it is not always possible to do the mathematical induction to prove things. So therefore, you also can have formal methods to do proofs, like the contraposition, the contradiction, the construction or exhaustion, or you have to check if you have a partial correctness, so that found result is really true, or that you have and you don't check the complete solution, or that you have a total correctness. So it finds a solution and it definitely terminates, so that you have really a complete solution for the whole classes. And it means that it must also hold. So algorithms which will run endlessly will not really solve a task. So therefore this is called the halting problem. So we saw now two special classes, and you can represent these special classes with these graphs. Again, in this theoretical inspection, you don't take care on, for example, different overheads or different additional runtimes if they are constants which you add. So therefore they have the same complexity class. For example, O of 1 is equivalent to O of k times 1, or O of k times n is, it doesn't matter if you have k1 or k10. So therefore this let's say overheads will not be taken into account. And we have now two special classes where you can directly see the general description of this big O notation. So you have the number of instructions, so it is not allowed to change with the problem size, or it's just a constant overhead. So it ignores these constant overheads, and it ignores also small constant factors, like on the right side, and it shows in principle the general growing of our behavior in time. So therefore we now just saw two very specific big O's, and I want to show you others. So which classification are usual? So other important complexity classes. You already know this, which is the O of 1, and you already know this, which is the O of n. There is one growing in between, which is the log n, the O of log n. And here I show you what does it mean. So you have the constant and the linear, and in between is the logarithmic. There are special implementations or special algorithms which solve, for example, constant is always an addition, comparison, so for example a if condition, or a recursive call. We'll come to this later. So if you can convert it to recursive call, then you win if you're here somewhere in the higher regions. The log n notation is, or the O log n is a normal element search in an ordered list, not the sequential search, but principal things in a search algorithm. This ON is element by element processing. Remember sequential search, or remember the sum. Then you can have the O of n log n, which is also logarithmic, but you have this n factor. This is a very effective element search. Or you have this n quadrat, so that you have this square O of n square. So it's a quadratic or squared behavior. It's already something like this. It's a very simple sorting mechanism. Then you can have a polynomial behavior, or you can have an exponential behavior. An exponential is really like this. So the quadratic is this one, and the exponential is really this. So it happens in the exponential that you really have, for short, small problems, you have almost a nice similar linear behavior. But then if you increase number, and from each step in the higher region to a next step, it will really jump in the behavior. So for example, for 10 elements, it can happen that it is really acceptable, but already for 1,000 elements it will kill your computer. And much more critical is then this O of k to the n. So this means that this is the worst scenario. So this is the best scenario, and down here is a worst scenario, which means algorithms will need more time, and even all programs, you will not be able to program in any language you want. You will not be able to program a solution for a case or class here which is very efficient, only for this. And therefore these classifications will also be classifications for the program solutions. If I show you this again, then with real numbers, then you will see what it means. We have a problem size for the different classifications, and I have here some sample times on the right. So let's go to O of 1. O of 1 means it's always the same. So if you have 4 elements, for example, if you watch here, you have 4 elements, then you will need 1 microsecond. If you have 1024 elements, then you even need just 1 microsecond. So log of n means that it's more by 1. It means, for example, if you have 1 microsecond, it will cost 2 microseconds in comparison here for 4 elements. So it's a little bit worse like this. But if you jump to 1000 elements like here, then you will need 10 microseconds. So there is already a big change to here. If you have n, it's twice as big as before. This means, for example, if you have 4 microseconds, then you will need 1.2 milliseconds. So this jump from here is tremendously. If you have a n log n problem, it's a bit more than twice as big as before. So you jump from 8 microseconds, for example, to 1.2 milliseconds again. It's a little bit more, so but it's the behavior from here to here, it's much better. If you have 4 times as big as before, then it's n squared, which means you have 16 microseconds for 4 elements. So if you always compare, 1 element costs 1 microsecond, 4 elements will cost 16 microseconds, but 1024 elements will even cost 1.05 seconds. And if you continue then to these 2 to the power of n, then you will see a tremendous change. It's the square of what it was before, which means for 4 elements you have now 16 microseconds, and for 1024 you have already 5 times 10 to the power of 294 years. So this means these algorithms are, in best case, the algorithms or the methods which are used for ciphering. So if you need this time of years to decipher a code, if you don't have the regional password, for example, then your algorithm is safe. So therefore, complexity classes like this give you also some hints. It's not just worse, they also give you some hints if a problem can help you in special situations, like for ciphering techniques. In the normal behavior for a runtime situation, it will be that you won't always reach a situation which is in the upper part of this slide here. So O of 1, O of n, or something like that. If I show you this in a graph, then you directly see what I mean with these cases. So a good algorithm, a good in runtime, so I already said that some of the things might also be good for other situations like ciphering, but in the runtime behavior, for a normal algorithm, a good algorithm is O1, O of log n, and so on. Even acceptable is O of n, things like that. Not so good, but still usable is O of n log n. And then we come into a region where we have a situation which is not really ideal. So every time when the growing starts climbing quite fast, it's not ideal. So it is here for the quadratic, for the 2 to the power of n, and also for the k to the power of n. So this is not usable anymore. So if you see here, everything, all algorithms where the growing is really fast, so jumps from 1 to, in this case, 8 elements or something like that, already changes the runtime tremendously, will change or will be not usable in normal runtime scenarios. In some cases, it's possible to change between the different classes. So you will find an algorithm which is in another class. If you change the way you do the work in your algorithm, but it's not always possible. So therefore, we want to have a look into the sorting algorithm, because there I can show you that there are possibilities to change between the classes, and both solutions will solve the problem of sorting elements. So what do? If we sort, we take a number set where we have an unsorted list of elements, and we want to convert it into a sorted list. So the simplest way here is we have numbers, we have real numbers, our integer numbers, and we want to arrange a sorted list so that they are ascending. The worst scenario, if you always directly focus on worst scenarios, is if we have a descending list. So for example, if we directly come to the idea to define a test scenario, in best case we will see the worst scenario if we have a descending set of numbers, because then we have to completely convert it to ascending set. A very famous, very simple example where we will do a similar thing like a sequential access, like in these access methods which we did in the tutorial, is here in the sorting method, the bubble sort. What is the bubble sort? The bubble sort has 2 for loops, and in principle it compares each element with each element. So it takes the first element and compares it always with the rest, and shifts it completely along all of the other elements. So all elements must be touched. If you have n elements, you will have to do n-1 touches, and this for all elements. So therefore, I can show you the sample, how it will work in Matlab, for example, if you have a completely descending list. So here's my list. I have 100 elements, and they are descending. So it's just a list of a continuous set of numbers, so that you start from 1 to 100, and at the end, after the sorting, I want it to be ascending. So if we do the bubble sort, then you will see it takes the first number and it compares it each time with all of the other elements, and it shifts it to the right. So in this case, each comparison is assigned or it's connected with a short break of 0.05 seconds, so that we see this shifting. But you see, it costs a lot of time. So there always, for each element, we'll have a comparison. So and we will not be able to wait on the result because it costs so much time. It's comparable to the sequential search, for example, because we always do these two loops, in this case for all of the elements. And you see it runs and runs and runs. Now we can think about the theoretical performance of such a method, of such a sorting method. So which big O notation would you assign to this? So therefore we take into account how many elements we have and how many comparisons or how many runs do we do. So if we have n elements, we'll have to do n minus 1 comparisons for each element. So what does it mean? We can calculate the number of comparison, or the class type, if we do the arithmetic progression. So we take the maximum number and the minimum number, we sum them up and multiply them with the maximum number, and then we divide it by 2. So in this case we'll come to a situation like this, and therefore we take exactly the largest term of our polynomial, which means we have the power of 2 as the largest term, and this is then the class. This is the most, or this is the element which influences our calculation mostly. And therefore we will have here a quadratic behavior. So if you compare this with time unit 1, and you have always for loops are comparable with sums, so therefore you have a double sum and you have a unit of 1, and if you calculate this you will get exactly this class type. So the dominating term is the quadratic term. So how can we improve now the efficiency? So how can we convert the quadratic term or the quadratic behavior into another behavior? And the ways to change the algorithm. So we jump from bubble sort to merge sort. And if you remember a method which I already explained in lessons before, it's a method of dividing and conquer. So it means you divide a larger set of elements into pieces, and then you work on the pieces and you just do a comparison, for example, in a smaller part, in a smaller region. And we did this already for the binary search, and here we can do the same. So we can use similar technique, so that we split it into 2 pieces, and then we go into the first piece and into the next piece, and then we split it again into 2 pieces, as long as we just will have still 2 elements, and then we just turn these 2 elements. And we do this for all of the pieces, and then we merge it together again. What does it mean? We start with a given raw data sample. So in this case we have 8 numbers which we want to sort. With these 8 numbers, we build 2 lists, in best case with 2 lists of the same size. So therefore in this case with 8 it's simple, we have 2 lists with 4 elements. And then we create again, we divide again into 2 pieces, into 2 lists with 2 elements, and then with 1 element. So we have a final stop criterion. The stop criterion says we stop with this division if we reach a list where only 1 element is given. So this is the part where we divide. Always we split into 2 pieces, and then we just take a look onto the rest what we have. And if we reach this situation, then we start the merging part. So what we have here is the dividing part, and then we do the merging. The merging means we take always the elements, we run through this given list to do through this given two elements, for example, in this case, but we take it as two different lists. So we take this list and compare it with this list. So let's go directly to here, where we have already 4 elements in the list. So what does it mean? We have 2 pointers, we have 2 indexes which run through these lists, and therefore we compare always one element with another element. So in this case we compare the 1 with the 3, and we always take the smallest one. So in this case we take the 1 and we go to the next element in this list. We keep here the position and compare the 2 with the 3. In this case 2 is small, then we take this and go to the next position. So we still are here at this position, so in the second list, and here in the first list we are here at the 7. We compare 3 and 7, so 3 is smaller, therefore we use the 3. Then we compare the next one, so we still keep the position in the first list, we go to the next position in the second list, so we take the 4 in this case. In this case we take the 5 and the 6, and then the list is empty, so we have no elements anymore, therefore we continue here and push the 7 and the 8 into the next point. So what does it mean? It is like we run with one for loop. So in this case with 2 pointers we run with 2 for loops, but it's like one for loop which runs through all of the elements which we have, and just all of these elements which come from the raw data. So at each of these columns here we run through all of our elements. So therefore what does it mean? We have the dividing part and we have the merging part, and if we take a look at our O notation, what do we have here? Remember, the binary search, or the binary elements, always have n half elements, n half elements, n half elements. So half, half, half. What does it mean? It gives a log n behavior. On the other hand, we always run through all of our elements. So all of our elements are n, 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 so n times n. So we have a O(n) notation. Together, we will have a log n times n notation. So O log n times O(n), which means finally we have a n log n notation. And this means that we have a behavior from here, from a squared class to a n log n class. So this is a worst scenario and this is a bad scenario. So we change from a really bad situation to bad situation, which is much better. And you directly see it if we jump into our diagram where you see the classifications. But it still helps if you have this situation of divide and conquer, or divide et impera, which means you divide and you will conquer the situation. Let's have a look into our diagram. So what does it mean? I jump to this position. So we come from one of these scenarios here, which is exponential, to a scenario like this here. So from very bad to bad. We still need a lot of time if we have a lot of elements, but we are much better than in a squared or an exponential behavior. So you will directly see this if I go to a Matlab program, and if you run this, you will see that it is really much faster. So this merge sort is really faster than what you saw before in the bubble sort. We start again with our nice descending list, and then I start the algorithm, and you will see always the divided parts and the comparisons which happen. The time which is assigned to each comparison is again the 0.05 seconds. So, and then let's start, and you will see that we can wait on the result. So you see we divide and then we merge again. So what you see is always the small list, and it's quite fast to have the complete list ready, finished. Compared to what you saw before with the same time constraints, there's a tremendous speed up. So therefore, merge sort is much better. There are other algorithms of sorting which improve the situation again, but I want to show you these two elements, or these two classes. So what we win with this is a very, very tremendous speeding up. And therefore, it's always ideal if you find a mechanism where you can divide a large set or a huge problem into small pieces, and then you just work on the small pieces and then you mix it together again. And this is called divide and conquer, or divide et impera. So you split, and because you split, you're the winner. Okay? So if you do this dividing and merging, or dividing and conquer, then you will come to a specific thing which can be done with functions. Do you remember functions have a special performance? And therefore you will come to this so-called recursion. Because if you go to this divide mechanism, at each position you do exactly the same. So you split into two pieces, then you split into two pieces, as long as you just have one element and another element which you directly compare. So you have one direction, you have a clear stop criterion, and then you do the way back. So you just connect the results. So each step here is similar, just with other inputs, also with the other input size, but because of these ordered lists which you have, if you have two elements which are ordered, so one element is always ordered, so you just compare two elements. And if you have two elements which are ordered, then you have again an ordered list. You just have to compare two elements to connect them. And therefore, all of these things can be described as a function. You have a clear end criterion. So the clear end or stop criterion is that you have only two elements which you compare, and then you do the comparison and you go back step by step. So we have this dividing part where you do exactly the same, and if you reach this end criterion, you do exactly the reverse mechanism to go back to the original set. And this is predefined for recursion. So what does it mean in the recursion? You call yourself and you use one specific thing which is defined for functions, that, for example, in a function, everything what is inside of the function will be available inside of this function. So every element, every memory which you create inside here will be existent as long as this function will not end. So therefore, if you call the function again, and if you hand over, so you call yourself again, and if you hand over another set, the original set from here will be kept as long as you come back from here. So you call the same function again with the left part, so you split it into pieces, and you call the same function again with the left part, and the same function again here with the right part. And then if you jump in again, you take this as a starting set. You go into the same function again, you split it into two pieces, and you call the same function yourself again with the left part and with the right part, so here. And then you do the same. So you split it into two pieces, and you call the function again with the left part and with the right part, as long as you have just two elements anymore. And then you start with a reverse part, with a merging. So this is the reverse part. So if you do this, you do it for both elements. So you start with the reverse part, and if you do it, if you have no left element anymore which can be split it into pieces than you do with a reverse part. This means that it is something like a staircase or a step function. So what you do is you start at the low level with a full set, then you split it, and at each level you do exactly the same. You split and you split and you split. But at each level, if you jump back, you will come to the same memory situation, and only things which you return from the function which you called, so from yourself, will be changed. So everything what you already have at this level, so everything what you reach here, will be kept. So if you call the function again, and if you come back, for example, from higher step, so you go up and you come back, then you have the new values and the already existing values. And if you call it again, because of the left part or the right part, so you do the left part, you jump up and you come back with the sorted list, and then you go into the right part, everything what is here now, so the left part which is already changed and the right part which will be changed, if you come back, it will be in the memory again, because it creates a stack where each call puts a new element on top of the stack, and it will be kept as long as you jump back to a previous step. And you have to return then what you changed to this step, so that everything what you had here before will be kept, and you can rearrange it with the things which you get back from the higher level. So it's jumping up, jumping down, and in each level you will have the same memory elements which you already had. And this is really helpful because you have now two functions, one with the divide and one with the merge. The divide is this recursive call. So what happens, you compare if the list has only one element. Therefore, if it has only one element, you return the number as the given list. If it has more than one element, then you do dividing into two pieces, and you give the one list, the first part of the list, to the function call again. So you call yourself again, and you call it with a new smaller piece of the original data, so with half of the data of the left and the right part. If you call this, it runs again through this whole step with a new situation. It compares, is there only one element in this list, and so on. If you have only one element in this list, it returns this number, and it will call finally, so it will return, and then it will finally call the merge. The merge is nothing more than one loop which runs through all of the elements, and it has two indexes. One points to the first list, the other points to the second list, and it just does a comparison, and if the one is larger than the other, then the smaller number will be used and will be rearranged, and it will return the new sorted list. And because it is only called with sorted lists, so if you have just two elements, it's already sorted, and then you rearrange it, and then you have a sorted list again, and you return this sorted list, and this sorted list here in the divide part will come back as a return argument, so it will be available after this call. And then you have here the sorted list, the sorted smaller list, and you can directly run merge sort merge, so this function merge sort merge again, and it will now rearrange these two already sorted lists into a new sorted list. So therefore you get again two sorted lists, and this is the trick. So you always divide first, and then you just use sorted lists anymore, and with sorted lists it's enough to have one loop through this whole stuff. So this is very efficient compared to doing this bubble search where you compare each element with each element. Again, let's have a look into this recursion again with a simpler program which does not make sense in a real world scenario, but which will explain a little bit better what we do here. So what we do here is we have a function which is called recursive, and we call this function inside of our function again. Each time if we call it, we start with this element, this handover argument, and we add a 1 to this argument. And then we start a loop from 1 to 3. We always display what we have as an output and which step we are. And if we reach, so this is the clear end criterion of our recursion. So if we reach a situation that the call hierarchy is not anymore lower or equal to 2, so if it is, for example, 3, then we won't do this recursive call again. So we will stop and we will go back, jump back to this position. And if we jump back, as we have no return, so we don't return calculations which we did inside, we'll jump to this level. Remember the staircase, so remember this step. We will jump to the step which we reached before. So everything what we calculated before will exist again, and the rest will be forgotten. So everything what we have done in the future steps or in the following steps inside of the next recursive steps will be forgotten. So what does it mean? If we let the program run with a starting sequence or with a starting number of 1, then we will start with call hierarchy 1. We have the loop counter 1. Then we'll jump into the next level. So we go to here, we have call hierarchy plus 1, so we'll have call hierarchy 2, and we'll run again to here. So we will start again the next function. So the loop will not continue. So it will just continue if we reach the end criterion. So the first steps are we count the call hierarchy 1, 2, 3, because these are the calls. So we have now 3 calls of our function. And if we reach the call hierarchy 3, then the loop starts. Our call hierarchy is always 3, therefore the loop will always continue. So we'll have 1, 2, 3. And then we finish our loop. We go back in function. So therefore we jump back 1 step down, and 1 step down we had the call hierarchy 2. So here we have the call hierarchy 2. Call hierarchy 2 is again plus 1. So we go plus 1 is 3. And then we start our loop again, and so on. We do this as long as we finish our complete run. Important here is that you get an idea of what happens, and I think this staircase, these steps are quite helpful, because each time if you step down, you will reach the situation again which existed before. Each time if you step up, you start a new processing, so you start a new calculation. And if you don't return things which you created in higher steps, you will lose them. So if you return them, you can keep it. Each time you jump back, you forget everything what you did in the higher steps. Okay, so therefore this is a recursive call of the same function. So you call the same function with a new argument, and each time if you come back, you will lose everything what you did, and you will continue at the step where you are with the next calculation, for example. You can use this method also for finding paths through a graph, and one very nice simple sample is this graph here, which is called the house of Santa Claus, because the children in Germany paint this on Christmas time, and they try to find a way through this graph. So they want to paint this house here with a method so that they have a continuous line, so they don't want to interrupt the painting, and they don't want to draw a line twice. So they start somewhere and they have to follow in one drawing the whole line, and they say this is the house of Santa Claus. So but this is a nice sample, because what you do is you start and you do at each state here, you do exactly the same decision. So I want to show you this. So if we decide to start here at the lower corner, at the lower edge here, then at this point I can make a decision. So I can go one way. So I can go up, or I can go here, and I can go here. So if I do a decision, then for example, I decide to go this way. So let's do this. Let's move up. So at this point, I do exactly the same decisions again. I know that I came from here, but I can go this way, or this way. So it's at this point here, I do exactly the same decision what I did at the previous step. And therefore, it's predefined for this recursion method. So let's do another decision. I want to go this way. So if I'm here, the same. I came from here, and I can make a decision. So if you remember, I always go, or if you watch this, I always go onto a direction which is not yet marked. So I remember, at each step for the next recursive call, I remember which direction or which line or which edge I already passed. So this is already marked, and then I go one of the edges which are not yet marked. So in this case, I just can go this way. And at this point, I do exactly the same. I know that I came from here, and I can go to here, or to here. So this is what I do. And at each point here, I do exactly the same decision. So I move through this graph, and at each state, I make the same decision. Each of this is one call of the function. So I call myself. And now I'm at a position where all of the graph edges which connects to me are marked. So I have no chance anymore. So this is my int criterion. And I found one solution, because I found one way completely through this graph. And what do I do now? I go the step back. So remember staircases? I go back, and at this jump back, I come to a situation again where the memory is like it was before as I was there. Okay? So what I have to do is I have to remember the path here so that I can use it later on. Because, for example, for the output, so if I jump back, I forget everything. So everything what I want to remember, so for example, that I found a solution, the counter for the solutions, and also maybe the path through this graph, I have to remember. And now I do a step back. So I go back to this point. So going back means I return from the function. Going back means going one step down. And I do the same again. Return, because at all of these positions, I just find solutions which I already have. So I have to remember where I came from, and I have to remember, or I have to check which positions are marked. At this position, I cannot go to here, I cannot go to here, I cannot go to here, and I came from there. So everything is already clear. I do this again. This is this jump back, this back step, or step back, and here's the same. I came from here, I cannot go to here, I cannot go to here. And again, jump back. So here at this position, I can start my recursion again, because it's the same decision as before. So the only difference, or the only thing what I have to remember, is that I came from here, and then I do the same decision. So this is already marked, so I just can go to here. So what I do is I jump to here, and then I continue in the same style. So this house of the Santa Claus is very connected to a thing which is called Euler's Königsberg bridge problem, because Euler defined this problem, and it's that you have here some islands. So here are the islands, and you have bridges between these islands. and you want to pass each bridge just once, but we want to find one path, one complete way, a so-called Euler way through the whole graph. So if you watch this, it's exactly the same. So let's start here, for example, at this island, and then I can go 1, 2, 3, 4, 5, 6, 7, 8, and I passed all bridges just once, and I found one way through this graph. And this is the Königsberg Bridge problem, which is really nice, connected to this house of Santa Claus. So Euler described such a situation in the year 1736. He found a proof that it is solvable if one island has an even number of connections, and then this is called an Euler way. So what we find here is an Euler way, and if it ends up at the same position, at the same starting point, then it's called an Euler circle. And this is the traveling salesman problem, or the Chinese postman problem. So if you pass all of the elements and you end up at the starting point here. So with this, you can solve all of these possibilities just with this backtracking algorithm. And therefore, it's very similar to this sorting algorithm. And it's a nice, effective way, but it grows with the problem size, of course. So if you have large graphs, it will not be very efficient anymore, because you find all of the solutions. But anyhow, you want to find all of the solutions. So you have to do all of the solutions. Compared to some optimization algorithms, for example, for navigation, you have then graphs which have weights on the edges and things like that, so that you have other decisions, and then you can find optimized ways. But anyhow, you always do the same decisions at the same, or at each point, and therefore it's again the same type of behavior. So this is just to explain what the backtracking algorithm here in this method of the depth first search does. We start with the first starting point, so we have to do all of these things for all starting points. If you remember, we started on the left lower corner. We have to do it for all of these for all of these states. So we start for all of this, but it's a loop over all of the states or nodes, and we start with the first starting point at the current position. Then we call the backtracking function, and then we go through all of the possible lines. We mark our lines, so we have to remember, we have to return things which we already marked, where we came from, and then if the current point fits to one of the current line endpoints, then we draw the line and set the corresponding line at a new way and go to the new point. The new point is then defined as a current point, and with this current point we go again into our backtracking function. So we call the backtracking function again and do the same again. If we don't find a possible way anymore, then we return. And this is our end criterion. And therefore you will have this way, which is very similar to what you saw from this simple recursive call. So each time if you jump back, you end up at the position which you had before. So everything else, what you did in the other steps, in the higher steps of our staircase, will be forgotten. So therefore you have to remember, and you have to remember the path which you found to give it back to your user and to tell the solution. Here is with an output of a colorization. So you have the starting point here on the left lower corner, then you go up, right, and so on. And if you find a solution, you remember the solution, and then you go back and you try to find a possibility again. So as you did this before, you don't do it, because you go to the next possibility, and you go back, you go back, you go back, as long as you find a new possibility. In this case, you came back from here, so you don't go this way again, but you have another possibility. You can go up here, and therefore you continue again with a forward step again, and then you go backward. So this is this backtracking algorithm. You can solve several problems of this. For example, you can find, or you can solve this Queen's problem, which you find in the lesson about style guides and things like that. So it's always the same class of recursion. And if you do all of this, you will find 88 solutions after scanning of 1,100 lines. If you watch the graph, you can improve this. If you find symmetries or whatever, then you can reduce the problem size, and therefore you can speed up your code tremendously. Okay, so you don't have to search all of the possibilities. And I want to show you the implementation in Matlab again. So here is the house of Santa Claus or Nikolaus. And if we start, I always paint the current line which we found in red. So if we start, you see the mechanism, and then also the step backward, and it finds all of these solutions. Each time if we have a green house, then or a house which green lines, then you have a found solution, and it goes through all possibilities, and it's nothing more than this backtracking or this recursive call. So each time if it deletes a red line, we go back, so it's a return from a function. Each time if we draw a red line, then it is a call of the recursive function. And you see it finds all of the solutions. So finally, we want to focus. This was the more or less theoretical part, and finally we want to focus on a real performance or real world performance, and also we want to think about the correctness of measurements. So how can we measure performance? We measure performance with time measurements, but these measurements are always influenced by other processes running on our computer. So therefore, one run is nothing. So the result of one run does not tell us anything about the real performance. It gives us a hint, so it will not change too much if the operating system does all of the preemptive scheduling tasks efficiently, but it will be influenced. Therefore, it's just a snapshot of the current situation, also influenced by operating system and other things. But how can we measure it? So you have already done this in the tutorial. If you did it, then you use the tick-tock mechanism, and tick is the start of a watch, and tock is the stop of a stopwatch, and then you will see the time. But as I said, it's just a snapshot. It will be influenced by the hardware, by the operating system, by active programs which compete in the process scheduling, by the of course by the algorithm complexity, or also by the implementation. So it's these constant offsets, which I said that I have in my algorithm for the merge search. About also the programming language or optimization in programming language can influence the real performance, and also the implementation and the data types, these data types which influence the implementation and things like that. So the real time costs can be completely different than the calculated costs in units, but the class of the algorithm will be the same. So what we do is we measure this tick-tock and we get a result. So what you always will have is the following. If you do a lot of memory accesses, then it will cost more time. So here's an example where we create, for example, the memory at the beginning. So here with the zeros, we create the whole matrix in the memory, and we just fill it up. So we just touch each element and we set the element. So we don't rearrange the memory anymore. Here we always rearrange the memory. So what does it mean? The first run creates one element, and then we do a new run. It will create a new memory element where it copies the previous one into this position and adds a new one with a size of 2, and it deletes the existing memory. And then we do a new run. We create now an element block of 3 elements. We copy the first 2 and we add the third one. So we have to delete the existing element block with 2. So we have a lot of memory accesses. And this means if you create memory at the beginning, so if you don't have to have a lot of communication between memory and CPU and rearrangements in the memory, it will be much faster. If you compare this, it's 3 times more what you need if you do it step by step. So even complex data types use heap memory. Remember the lessons before. Heap memory must create memory elements. So there's a lot of work, a lot of things. You can always go back to the John von Neumann architecture. It's not the best explanation, but each time if you leave one of these blocks, remember input, output, memory and CPU, each time, and you have lines between, each time if you leave one of this block will cost a lot of time. So each time if you have to do several memory accesses between memory and CPU, or if you have to read something from the input or write something to the output, or write something to the monitor, or write something to a file or to the internet or whatever, each time if you pass these blocks, you will lose time and it will cost time, and therefore you will increase your costs. So therefore directly avoid this. As long as you know how much how many elements you need, directly prepare the memory and then just fill it. Things like that. Another thing is, if you, for example, write your own loops, and if you do an element by element operation, the functions in Matlab are always optimized, and therefore they can directly work on complete memory blocks. So in this case, we calculate the sinus, and we calculate the sinus element by element, or we calculate the sinus over a whole vector. And if you compare this, the loop where we do an element by element calculation is tremendously more cost intensive than the direct calculation. So always use Matlab functions because they are programmed inside with optimized memory accesses. Other things are as well if you write something to the output. So if you write something to the monitor, to the command window. If you use the colon, semicolon or not, means you write something to the output or not. Each time if you have to write something, it will cost much more time. So avoid this as often as possible and always use this semicolon situation. And then you have to test your program, of course. So in real world scenarios, it's quite difficult to test all possibilities. If you do a theoretical inspection, then you can get the class of the algorithm, but it does not tell you exactly what you need or which costs you produce if you do a special implementation. And therefore you have to test everything. remember the test cases, things like that, so that you have a special behavior. They always test a partial correctness, and therefore you have to think about what can you do, or how can you improve your program to really test situations which tell you something about the correctness and also about the behavior, the runtime behavior. And this is done with the use cases or with the unit tests. With these use cases which you define for the unit tests, you define a test function or a function under test, and you feed this function with special inputs, so with special test cases. And these use cases define the test cases which bring your program into critical situations. Remember, if you did the tutorial, you tested it with the limits, so with the largest and the smallest number, or with numbers outside of your data set. So this is always ideal. It's just a partial correctness and a partial test, but it is always a nice test if you do the limits. Run into limits, min max values, extreme values, illegal values, and if you want, you can also do randomized values. A professor told me the best test is if you sit your grandma or grandfather with no experience of computers in front of your program and let test him the program by pushing any button. So this is a randomized test. And then you run the function under test and you check what happened. So you test these limits and you check what happens. Do you get wrong results? Do you have crashes? Do you have leaks? For example, you watch also the space, the memory consumption, things like that. And you can also watch the performance, the benchmark. Do you have with limit values a very worse behavior so that the costs increase tremendously? Or does it work as expected? So therefore you have the connection point between the theory and the practical parts. And if you remember, you connect here with these algorithms a lot of other lessons. So the performance, things which influence in real world from the operating system, our behavior here in the algorithms implementation, things like that. So it touches a lot of things. So the real implementation or the real computer science, applied computer science, requires knowledge in a lot of other parts of computer science. And therefore, we had all of these lessons before. That's it. So this is what I wanted to tell you about algorithms. So we'll see each other in the tutorial about algorithms and in the next lessons. Stay safe. And I will disappear now.